Hello and welcome to all the viewers. So in this video we will going to discuss about material properties required as per FE analysis type. So all of us know that we need to provide few material specifications or properties in order to perform the simulations. But do we know that we need to keep same material details for all analysis type? So in this video, we will going to discuss about what are the minimum material details which we need to require to perform the various FEA simulations. So this slide represents the learnings in this video. The very first we will going to discuss about what are the major material properties that we will need to perform the FEA analysis. Okay, so basically Young's modulus and the Poisson's ratio. These are the two major material property details which we need to perform the FEA simulations. Then next we will discuss about the material properties required as per different analysis types. Okay, so we will going to discuss all this. We have already created a blog on that and I will going to share in front of you so that you will get a complete overview of what are the minimum material details which we need to enter while performing the simulations. In addition to that, we have a different materials like bilinear or material test data. So how to enter that? Then we have a gasket material like compression, linear unloading, non-linear unloading. In addition to that, we can define gas stack by another material method, that is hyperelastic material. So how to perform that, or sorry, how to input all these material details in ANSYS we're going to discuss in this video. So what we will do now, we will go to our blog. There we have created this blog post and there we will discuss this present video. So basically when you input this material details in ANSYS, you will find this such kind of graphs in your ANSYS. Okay, so these graphs are automatically created based on the values which you will going to provide for a stress strength. So now let's go to our blog post and there we'll discuss the things. So now if you see that this is nothing but our blog, that is www.graphengineering.com. So from here you just need to refer the respective blog post. So basically it is like material properties required in finite element analysis. So if you click on this, you will find that we had already covered the complete point which we discussed earlier. Now let's start with the first. Like as we know that there are different material properties are present to represent to any material. So like when we talk about material, let's talk about SS3 stainless steel. So you may have Young's modulus, Poisson's ratio, mass density, thermal conductivity, then thermal expansion, specific heat, stress strain curve, fatigue life curve. In addition to that, you will also have like what is the compositions if you have alloy steel, and then you have bulk modulus, shear modulus. So all these details you will have. But when in order to perform the FEA, do we need to enter all this material to represent the FEA? So for that we have created this blog post. So if you see this, the very first we know that the most popular simulation, that is linear statics. So when we talk about linear static and to represent any material, you just need to define the Young's modulus as well as Poisson's ratio, and sometimes you need to define the mass density. So if you see here we had created a star mark. So what does it represent? It represents that, so when we are the mass density only required if you have mass elements in the analysis. Suppose if you have few components which you have idealized with the help of mass elements, or you can say the in FEA we used to call it as a mass element. In other softwares you will find that different element types. Basically it is a simple point element, or you can say the mass, where we apply the concentrated mass of the components which we need to idealize. So basically it is created at the CZ location and it is attached to the respective mounting points. So in such a case, when you are idealizing any body, in that case you need to define this mass density in order to consider that respective masses. If you don't have any idealized mass, then you only need Young's modulus and Poisson's ratio. Then the next thing, that when we talk about non-linear contact, so in that case also there is no need to define all these remaining details. Then what is the difference between non-linear contact and non-linear material? So as name suggests, here only you need to define the non-linear contact. So it might be your frictional contact, it might be your rough contact, it might be your frictional less contact. Okay. Now when we talk about non-linear material, here you need to define this stress strain curve. So similarly for non-linear dynamics, so this is basically non-linear dynamics. You just need to enter, or we can say the explicit simulation. In that case you will need impact, drop, Young's modulus, Poisson's ratio and mass density. Similarly in fatigue also you will need Young's modulus, Poisson's ratio, mass density, and here one additional thing you will need, that is SN curve, that is your endurance limit curve, fatigue life curve. Now let's talk about linear dynamics. So basically the vibration simulations, so such as model, seismic, frequency response. So in that case you will need the first three details, that is Young's modulus, Poisson's ratio and model mass density. And when we talk about thermal, so there only we will only need a thermal conductivity. So basically here we are only interested to see the thermal gradient, so that can be easily captured with the help of thermal conductivity of the material. Okay, so basically conduction, convection and your all three heat transfer you will going to see through this thermal conductivity behavior and the contacts between the different bodies. Now when we talk about thermal structural, there we will need one more additional detail. So basically you will need Young's modulus, Poisson's ratio, mass density, and in addition to that here you will need thermal expansion also. We need to change that, but here in order to see the thermal behavior, or you can say the thermal displacement, whatever you perform in the thermal simulation, that can be captured with the help of thermal expansion. So basically you will need here, instead of this you will need a thermal expansion. Okay, and then next you will furthermore need the another analysis type, that is transient. So when you have a time dependent data, in that case you need to define the specific heat. Okay, so you can see that specific heat, this is the additional simulation material detail which you need to perform when you are doing any transient simulations. Okay, so like that, as per the different material details, there is two common material details, that is Young's modulus and Poisson's ratio. So in here we already covered what is Young's modulus. I think most of us know that what exactly the Young's modulus. Okay, now you can see that this is nothing but a simple stress strain curve. For linear simulation we just assume that this stress curve is linear. You can see this dotted line, but when we have a non-linear curve, then we need to define this stress strain curve after the your elastic limit. Okay, which is the more accurate simulations. Now you can see that we already covered that in figure 1. If you want to calculate the respective Young's modulus for this respective point, so you can see from 300 megapascal and 0.0015 strength. So basically you will get this your Young's modulus. You can easily calculate it with the help of this. And in addition to that, you can also see this Poisson's ratio details. So what is over here? We already discussed the Poisson's ratio, which is basically used to see the how the respective object is deforming, or you can say the it is performing expansion or contraction based on your thermal or any other loads, that can be easily captured with the help of Poisson's ratio. Now in addition to that, you might have seen that non-linear, there we need to define the stress strain curve, but there are few material details. Sometimes you have a material details in the form of some stress strain data, but not as a stress strain curve. You will have something like elastic plastic or elastic perfectly plastic. So that is basically called as a bilinear isotropic or kinematic hardening models. So when you have such a kind of materials, how to define that in ANSYS, we will discuss after this blog post. Now similarly, if you have different materials with a different multilinear profile, so you can see that it is somewhere here like this, then it is changing. So like you will find there are 4 different material profiles are there which are changing drastically, so that is called as a multilinear isotropic. So here if you have some kind of stress strain data which is available from the testing, so you need to refer this to perform the simulations. Now in addition to that, sometimes we need to perform the gasket simulation also. So in that case, gasket simulation, in addition to that Young's modulus and Poisson's ratio, you need to define a few additional material details, such as you need to define the compression curve. So basically it represents the gasket behavior. So now we can see that the pressure versus closure, so it just, you can see that it is gradually increasing. With the increasing your distance, its pressure got increasing. Similarly, you need to define the linear as well as non-linear unloading curve. So here you are defining the loading one, and then here you are defining the unloading. So basically it represents the gasket behavior. So perform the respective gasket simulation, you will get this data from your respective manufacturing catalog or from the testing data. In addition to that, we also have some material details, like this gasket simulation or any other rubber simulation can be easily defined with the help of hyperelastic. There are different methods are available to perform the or to represent the hyperelastic materials, such as like Neo-Hookean, origami or EO method, or you can see that Muni or polynomial method. But the simplest one you will find that Neo-Hookean. So here you just need to define two different constant like inertial shear modulus and incompressibility parameter. So this you will easily get with the help of your hyperelastic material Shore hardness. So like when we talk about gasket, so it is basically Shore 40 kind of thing. So based on that you can easily calculate these two constant, and then you just need to enter these two constant to represent this hyperelastic material. Okay, so like that you just need to define all your materials when you are performing the respective simulations. Now what we can do, now we can go to our ANSYS, and there I will show you. So now by default you will find that structural steel is there. Now if you want to define, so here you can see that you have bilinear isotropic. So let's discuss first how to incorporate nonlinear material. So like here, go to engineering data source. So there are few general nonlinear materials are there. So I will just going to use a structural steel nonlinear. Just add this. You can also see that aluminum nonlinear, and then go over here. So once you will click over here and aluminum nonlinear, you will sign this bilinear isotropic hardening. So basically it is nothing but your stress versus strain. Similarly for this you can see that bilinear stress versus strain. Okay, now in case of linear material there is only two different, this Young's modulus and Poisson's ratio are sufficient. There is no need to define all this remaining material details. Okay, this is all about your bilinear isotropic model. So let's see that if you want to enter this what we discuss here, the very first, that is your elastic plastic or elastic perfectly plastic. So to define that you just need to click. So I will just add some material here like SS. Okay, and this SS, let's first define the density, then let's define density. I will just enter a rough value, that is 7850, which is basically for a steel, and then okay, just click over here and then define some isotropic elasticity. So let's define like 210 E3 and Poisson's ratio as a 0.3. okay, so basically if you have Poisson's ratio more than 0.4, so you just need to say that this is your non-metallic gasket, or you can say that your plastic or others may have higher Poisson's ratio compared to your steel or linear material. Then let's see that okay, SS. Now if you want to define bilinear, so just click over here and you can see that here once you just need to define your yield strength. So let's define like 250, and if you have some tangent modulus, so you can define like I want to define 1. So if you click here, you will find that your tangent modulus like 15, right? So like that you can define your tangent modulus. So when you are saying that elastic perfectly plastic, in that case your tangent modulus is 0. Okay, when you are saying your elastic perfectly plastic, so basically this one, blue color. Now if you have some elastic plastic, so in that case you just need to define few of the tangent modulus. This is all about your bilinears. And next one, how to define this multilinear. So in that case you just need to go over here and double click. So here you will find that your plastic strain versus your, so here you just need to define as per, let's put 0, let's define some 100, let's define here 0.2, 250 and give 0.5, 350. Okay, similarly if you have another 0.6, 500, like that you can define your stress strain curve. So basically here stress versus your plastic strain, you are defining to define your multilinear isotropic hardening material. Okay, now let's talk about the another material graph, how to enter the gasket material. So for that if you want, you can even see here engineering data source, and here you have few non-linear material. By default you will have gasket linear unloading. You can see what we discussed, that is pressure versus closure. Gasket non-linear unloading, so you can see that. Okay, and suppose if you have testing data, then if you want to enter uh, here, so you just need to go to the gasket section. So let's see here gasket section, and here click on the double model, double click on the gasket, and here you will define your compression curve. So let's define the temperature as a 20, and here you can represent your pressure versus closure. So let's, like 1 mm I can put 100, 2 mm I can put 250, 3 mm I can put 300. So like that you just need to define your here closure, pressure versus closure curve. This is basically for a linear loading. So what we saw that this is compression, this is basically for a compression. Now let's talk about if you have some data for linear unloading. So you just need to define furthermore 0.00, 0.001, and here you just need to define your slope. Okay, similarly 0.003.2 kind of thing. Okay, or if you want to megapascal kind of thing. So whatever the details you have, you just need to enter in this to define linear loading or versus unloading. Similarly, I will delete this. So based on your data, you just need to refer the gasket model, and from there you can define your respective gasket material details. Okay. Now we discuss about how to define bilinear, multilinear, then compression, linear, non-linear loading. We also discuss about how to define stress strain curve. Now the last topic is how to define the hyperelastic material. So for that you just need to go to your hyperelastic module. I will see here, and here you will find there are various methods are there, but the simplest one is Neo-Hookean. So here you just need to define your two dates. So let's expand this and let's put megapascal. I will put like 0.3 and here 250. Okay, so based on that you will find that it automatically creates the stress strain curve. Okay, so that is about your shear modulus and your incompressibility parameter. Based on your Shore hardness, you just need to refer some analytical formula just to calculate these two constant, and then you just need to enter and you can represent your respective hyperelastic material, basically respect to your gasket material. Okay, So this is all about your material details. Now if you have some additional details like creep, so you can even define that creep details from this respective graph. Now if you have some custom material models, you can define from this. If you have some fractures like linear fracture, bilinear fracture, so just to perform the fracture simulation, so in that case you can define from here. Now damage and these additional things are there which are basically for other simulation types. Like when we talk about fluid structure interaction, in that case we will need all these details. And if you have fatigue, then in that case you just need to define stress strain curve. So here you just define the stress versus your strain curve, okay, from here. So that's it guys, that's it from my side. Here we just discuss what are the minimum material details which you need to enter to perform the respective simulation. Also we discuss how we to enter this, ANSYS, like bilinear, multilinear stress strain curve, how to define gasket material, how to define hyperelastic material. So let me know your comments. I will be there to help you. Thank you. Bye bye. Take care.